Thanks for watching AI Weekly Update from Henry AI Labs. This weekly update will start off by looking at Microsoft's Zero 2 blog post. In their original paper Zero that powered the Turing NLG 17 billion parameter language model, they implemented phase 1 of the Zero Redundancy Memory Optimizer, which was the optimizer state. Now they've implemented the gradients and the activation memory optimizations as well. And in their blog post, it describes that this enables them to train 170 and 200 billion parameter language models. We'll also look at open sourcing BIT. Google has performed this large-scale study of training these massive representations on scaled-up datasets like ImageNet 21K with 14 million labeled images and JFT 300 million, and they've explored miscellaneous details of how to fine-tune these representations onto downstream tasks. So now they've open-sourced the BIT medium-sized 152-layer with multiplier of 4 ResNet model. Then we'll look at OpenAI's remarkable demonstration of code generation with the GPT-2 style model, such as filling out the function def is palindrome, and then the docstring and the code completion model is able to write the function. Finally, we'll look at the Facebook new marketplace features like the GrokNet for product recognition and being able to get three-dimensional views of a two-dimensional image. Then we'll look at making sense of vision and touch, a really interesting article from the Stanford AI Lab blog that describes training this multimodal representation with self-supervised learning. Then we'll look at OmniTact, a multi-directional high-dimensional touch sensor from researchers at UC Berkeley's AI Lab. Then we'll look at grounding language in play, an interesting approach to having goal-conditioned policies that perform tasks based on natural language instructions. Then we'll look at simple sensor intentions for exploration, a new technique from researchers at DeepMind that tries to deliberately control the sensor inputs. So for example, trying to burn your hand or trying to read in a certain force sensor or visual color distribution. Then we'll look at universal adversarial perturbations, exploring these one noise mask that can be applied to multiple images to cause misclassifications. And then we'll look at feature purification, which explores what happens to these features in deep neural networks after they've been trained on adversarial examples as well, showing differences in features like diagonal lines and other kinds of features where you can see clear differences between the features before and after they've been trained with adversarial training. Self-supervised learning in NLP is a visual guide to different tasks like autoregressive language modeling or emoji prediction. Then we'll look at a project from Machine Learning Reddit AI-generated archive papers, which discusses using the Kaggle-hosted dataset to generate artificial titles and abstracts. Then we'll look at a demonstration of the next word prediction, where you can explore what BERT, XLNet, or Roberta, Electra, or BART would predict on the next word given some input, as well as the mass language modeling task. Then we'll look at on the value of out-of-distribution testing, an example of Goodhart's law, which is an example of troubling trends in machine learning scholarship and showing how you can gamify this kind of out-of-distribution generalization test. We'll look at a talk from Francois Cholet on Keras, the next 5 years, that discusses interesting directions for the future of Keras, like automation, scale in cloud, and into the real world at the Scaled Machine Learning Conference. Finally, we'll look at this tutorial on the Stanford question answering dataset in Keras. If you haven't already, please check out this week's edition of Machine Learning Street Talk, where we interview Harry Valpola, CEO and founder of Curious AI. In this talk, we continue our discussion of System 1 and System 2 deep learning, as well as model-based reinforcement learning and its applications to industrial control processes. Over the course of February to November 2019, OpenAI gradually released their GPT-2 language model, fearing the spread of misinformation that these large-scale language models could be capable of, going from 124 million parameters to 355, 774, and finally 1.5 billion parameters. In February 2020, Microsoft announced the Turing NLG 17 billion parameter language model. The workhorse behind Turing NLG was the Deep Speed Training Optimization Library and Zero, the Zero Redundancy Optimizer. Scaling up technologies like NVIDIA's Megatron, recently responsible for a 3.9 billion parameter BERT model, focus on model parallelism and the best way to split a large model across multiple GPUs or accelerators. Zero focuses on how to reduce memory redundancy. The article describes how much memory different components of training deep learning models require, such as the optimizer state, gradients, and activation memory. In 0.1, the original optimizer that trained Turing NLG, the researchers had implemented phase 1, partitioning optimizer states. Now, they've implemented the gradient and activation memory optimizations as well. 0.2 achieves the fastest BERT training record of 44 minutes on 1,024 NVIDIA V100 GPUs, beating the previous record of 67 minutes held by NVIDIA's Megatron. With regard to building skyscrapers that take us to the moon, the blog post writes that they're capable of efficiently running models of 170 billion parameters, testing with 400 NVIDIA V100 GPUs. With more devices such as 1,000 GPUs, 0.2 allows us to scale towards 200 billion parameter language models. The Big Transfer BIT, General Visual Representation Learning Model, is a push to align the computer vision and natural language processing workflows. In a similar vein that a text classification model would start with BERT pre-trained on a large language modeling dataset, this research suggests a similar direction for vision models. This animation depicts the fine-tuning pipeline of taking this pre-trained representation and attaching new classification heads for new tasks. This blog post announces the release of the BIT medium-sized model, an 152-layer ResNet with a width multiplier of 4, trained on ImageNet 21K, and tutorials in JAX, TensorFlow 2, and PyTorch to use it. ImageNet 21K is an expanded version of ImageNet with 14 million images labeled into 21,000 classes, compared to the original ImageNet that has 1.28 million images in 1,000 classes. Fine-tuning BIT on your task of interest can come with a lot of hyperparameters such as the learning rate or weight decay. In this paper, the authors also devise a BIT hyperrule table, which prescribes the fine-tuning hyperparameters based on heuristics of your dataset, such as the image resolution and the number of labeled examples. This is tested on more than 20 diverse tasks ranging from natural to medical images. The blog post further details findings of the study, such as replacing batch norm with group norm and weight standardization for pre-training at scale, similar to last week's discussion of how Megatron BERT rearranges the normalization layer for training at the 3.9 billion parameter scale. The blog post also describes the benefit of scale for the few-shot learning setting, testing this on different scenarios in CFAR 10 with 1 or 5 labels per class. The blog post also discusses the relationship between model and dataset size, which Yannick highlights in his video explaining BIT looks like a result of the double descent phenomenon. At Microsoft Build 2020, OpenAI demonstrated a remarkable ability for intelligent code completion with models such as GPT-2 trained on code. There hasn't been a research paper released along with this, but you can see some impressive demonstrations, such as filling in a palindrome function from the doc string. Yannick has made a video exploring the news, including a more nuanced fill-in-the-code example from OpenAI that Yannick couldn't find anywhere on GitHub. Facebook is launching really exciting new features in Facebook Marketplace powered by computer vision. This video from Tamara Berg describes how an AI lifestyle assistant could recommend a lamp for your apartment. This is powered by GrokNet, a system for recognizing products in pictures. Interestingly, this is trained with 83 loss functions, 80 categorical, and 3 embedding losses on 7 datasets. This video describes alternating between weak supervision, such as using hashtags for labels, which was also explored in Facebook's billion-scale semi-supervised learning paper that had achieved ImageNet state-of-the-art when it was released. The blog post also describes their model's ability to automatically construct 3-dimensional views from a 2-dimensional image, such as this guitar, to get a better showcase of products. The Stanford AI Lab blog published Making Sense of Vision and Touch, Multimodal Representations for Contact-Rich Tasks, describing their paper for peg insertion, where there's a different shape like a triangle, circle, or square that the robot has to put into the equally shaped hole in the wood. The authors start with the example of closing a water bottle. Our eyes tell us the pose and geometry of the bottle, and our sense of touch tells us texture, pressure, and force information. I think a better analogy might actually be opening the water bottle, because it's impossible to see how tightly screwed on the cap is. The authors include a video with their submission to ICRA, International Conference on Robotics and Automation, that shows an example of how the force sensor spikes when the robot first makes contact with the wood. Their algorithm combines force and vision information with a late fusion technique. There's a separate convolutional encoder for the vision input and a separate WaveNet-style dilated convolutional network to encode the force sensor readings. The authors describe additional differences in these inputs. Force or torque sensor readings only have 6 dimensions compared to the high-dimensional pixel maps, but they have the complicating quality of rapidly changing. When the robot's not touching anything, the sensor registers 0 newtons, but that can quickly jump up to 20 once contact is made. So after separate networks encode the vision and force modalities, these features are later combined in the pipeline, described as a multimodal representation. The authors use self-supervised learning to train this multimodal representation, predicting things like the optical flow of the images, the next pose of the robotic arm, will it make contact in the next step, and determining if the sensory inputs are time-locked with each other. I think this is a really interesting paper and blog post about combining vision and touch. I think it's easy to imagine tasks such as opening a water bottle that would benefit from touch as well as visual information. Berkeley's AI Lab blog has posted more details about their OmniTact touch sensor, particularly contrasting it with gel site sensors that have been used to insert a USB cable, roll a die, and grasp objects. The blog post describes these high-resolution, tactile images. OmniTact uses cameras embedded into a silicone gel skin to capture deformation of the skin. The blog post further describes learning to plug an electrical connector blindly into a wall purely based on information from this touch sensor. Grounding language in play tackles the ambitious goal of a robot that can perform any task and is generally useful as an everyday robot. In order to achieve this, we need general task specification, the ability for untrained users to direct agent behavior using the most intuitive and flexible mechanisms, such as natural language. We've seen a similar effort in natural language processing with the text-to-text input-output formulation led by research such as the T5 text-to-text transfer transformer and the natural language decathlon. This is challenging for current robotics because certain commands require massive decompositions and vision language grounding. Imagine a command such as sweep the block into the drawer. The robot needs to know, what does a block look like, what is a drawer, and what commands do I send to my arm to sweep? The authors continue their work on learning from human-controlled, teleoperated data to perform goal condition policies, extending it to language conditioning and grounding language in play. A goal condition policy is where an agent conditions its policy such that it's trying to perform a specific task rather than maximize reward in the same task environment pair. Some examples of this are how in First Return Then Explore, the latest installment to Go Explore, the agent is goal conditioned to return to its original state. Another similar experiment is upside-down reinforced learning, where the agent seeks out a specific amount of reward in the environment. The authors of Grounding Language in Play train this agent first in the teleoperated play dataset, then play is paired with human language, and the agent alternates between solving image and language goals for training, and then only solving language goals at test time. If you're interested in learning more about this, they've also made a GitHub page with animations in addition to the paper. Simple sensor intentions is a new exploration technique from researchers at DeepMind. The idea is to seek novel state sensings, but this isn't quite the same as, say, novelty search, where the agent receives an intrinsic reward for hitting a new state, or plan to explore, where the model uses a world model to pursue states that have high uncertainty in the world model's prediction. The idea in simple sensor intentions is to deliberately pursue a sensor reading, such as a color distribution in our vision input or a force reading on the force sensors. Imagine deliberately trying to figure out how to burn your hand in your house. The authors show pursuing sensor values results in successful exploration, writing, in the absence of an external reward signal, a sensible exploration strategy can be formed by learning policies that deliberately cause an effect on the observed sensor values by driving the sensor responses to their extremes or by controlling the sensor readings at desirable set points. Adversarial examples are a troubling discovery in deep learning, the most famous example being the addition of this noise map to the panda image that causes a classifier to classify this as a gibbon with high confidence. This survey paper explores image agnostic perturbations. This is in contrast to per instance adversarial examples. This image shows an example of a noise map that can cause misclassifications when added to several images. Feature purification explores how adversarial training changes the features learned by deep learning models. The authors show that the existence of adversarial examples are due to the accumulation of certain dense mixtures in the hidden weights and show how adversarial training purifies these features, such as this example of going from 3 to 1 diagonal line in a given feature map. If you're interested in adversarial training, I recommend checking out Adversarial Examples Improve Image Recognition, which achieves huge gains on ImageNet and the miscellaneous subsets of ImageNet. Amitness has published another visual illustration of concepts in deep learning, this time tackling self-supervised learning in NLP. The tutorial starts with a description of pretext tasks compared to supervised learning, and then describes several formulations of self-supervised learning in NLP, such as center word prediction, neighbor word prediction, neighbor sentence prediction, autoregressive language modeling, masked language modeling, next sentence prediction, sentence order prediction, sentence permutation, document rotation, and emoji prediction, linking to Deepmoji, an interesting paper where they use a dataset of 1.2 billion tweets to predict the embedded emojis. This is done to provide an additional signal for sentiment, emotion, and sarcasm detection. On the subject of self-supervised learning in NLP, here's a really interesting GitHub repository that implements a visualization of next word prediction. You can type in a sentence and see how BERT, XLNet, XLM Roberta, BART, and Electra predict the next word, and you can also include mask tokens in a sentence to see those predictions as well. I came across a really interesting project on the machine learning Reddit that aims to generate archive papers, or at least just the abstract, from a dataset of 31,000 papers by fine-tuning GPT-2. The blog post describes the 6-stage process of downloading the papers from the Kaggle-hosted dataset, fine-tuning GPT-2 on the titles, filtering these titles based on duplicates in the original dataset, then separately fine-tuning a GPT-2 on the abstracts of papers in this dataset, and then in the end, the fake titles are used as the seed for GPT-2 to complete the abstract from there. You can visualize this on boredhumans.com. On the value of out-of-distribution testing, an example of Goodhart's law shows another example of troubling trends in machine learning scholarship, where the lack of a validation set has caused gamification in out-of-distribution visual question answering contests. They highlight the problems with this formulation of out-of-distribution generalization, where the test distribution is just the inverse of the training distribution. This is an example of the distribution of these answers in the training and test sets for labeling sports and counting people in an image. This week, Francois Cholet's talk at the Scaled ML conference in late February was released on YouTube. This is a really interesting talk where Cholet describes how he thinks of TensorFlow and Keras and 3 directions for the future: automation, scale in cloud, and into the real world. I'm excited about Keras Tuner and AutoKeras for automation, and I highly recommend watching this talk. The Keras examples page has been releasing some really great tutorials, including this one on using an 110 million parameter pre-trained BERT model from Hugging Face in Keras. Most of the tutorial is describing how to load and pre-process the Squad Stanford question answering dataset and setting up the exact match callback metric for evaluating extractive question answering models. This is a really great example of how to parse one of these datasets and then how to implement a custom callback to evaluate a model on something like question answering.